the material behavior. This is now bringing together stress and strain. Material behavior, this is the major subject where we wanted to get to, but before we had to do all these mathematics tricks, definition of stress, what you can do with stress, definition of strain, what you can do with strain, and only now we can bring them together. So you will have to remember now everything from the previous days, from index notation to tensors to working with it to stress and strain. Okay, so now quickly repetition. What is the strain? And I'm using one component of strain only. That is the change of length. New length divided by old length divided by original length. Old, the same. Okay, so that's the definition of strain. There is a relation between stress and strain, which you should have seen already, maybe without the indices, maybe just epsilon equals sigma divided by E. Now, since we talk about tensors and since we talk about three-dimensional objects, we have to specify the direction. And we know now that a normal stress on the one side of this rectangular object, previously it's a cube. In the deformed situation, it's a rectangular deformed shape. So the sigma 1,1 is the stress on the right side, and in equilibrium it will be the stress on the left side in the absence of other stresses. Okay, and that one is force divided by area. That one is the engineering strain. Sorry, that one is the engineering strain as I defined it. Correspondingly, it's the engineering stress if we use the initial area of the undeformed configuration. It becomes the true stress if we use the deformed area. This one becomes the true strain if we relate or if we integrate the incremental strains. Then it becomes the true strain. And the true strain is referring to the momentary area and length. The engineering strain is referring to the undeformed one. So that was repetition of true and engineering strain, the difference between the two. Okay, now back to the stress-strain relation. Strain here is expressed as a consequence of a stress. So if we apply a stress, if we apply a force on this object here, force per area is stress, so then that is the action which we do, and the reaction is strain. Okay, and what mediates between the two, that is the Young's modulus, and that one you definitely have heard already about. Okay, now, and in tensor notation, we will use all the indices later, but here in this situation, when we stretch some object in the one direction, then we talk about normal stress 1,1 and normal strain 1,1. Now, next slide. The lateral strain, that is then the strain which is the change in the two direction, and the 3 is the strain in the three direction. Now, any arbitrary object, if we deform it in the one direction as indicated here, so the action is sigma 1,1, the reaction is epsilon 1,1, that's the direct reaction, but there's also a perpendicular reaction, and that one is quantified by the Poisson's ratio, or in Dutch, the dwarscontractiecoëfficiënt. I had to practice this so often that I like to repeat myself to stay used to it. And the Poisson ratio, that one is epsilon. That one is defined as epsilon 2,2 equals the action which we have on the right-hand side, sigma 1,1 over E, times minus mu. Mu is the abbreviation, the symbol for Poisson ratio. Epsilon 3,3, same thing. And they are equal only if we have isotropic material. And in my lecture, we talk about isotropic material all the time. So that one is true also, not in general. Okay, so now we have a reaction perpendicular to the stretch direction, 1, and we have a direct reaction to the stress which we apply. So that's Hooke's law. That is what we refer to linear elasticity, and Hooke was the first one to whom people attribute the formulation of this. Okay, but that was, and you can guess what comes next, that was only the one direction. Action in one direction has a reaction in the one direction, direct, and a perpendicular one in the other two directions. And for isotropic material behavior, this is the summary of what I just said, nothing new. And by the way, shear strains remain equal to 0. Now, when you apply another action, for example, a normal stress in the 2-2 direction, then you get a reaction in the 2-2 direction, that's the direct one, and the perpendicular indirect one in the perpendicular directions. And for 3, 3. No big surprise here. Okay, so the combined stress is the 3 actions are a combined stress, 3 normal stresses, and that gives us 9 reactions. This is not yet the 9 from a tensor, but this is just one action gives 3 reactions. This action gives also 3 reactions, this one also. So we have 3 actions, the 3 normal stresses, 9 reactions, the 9 contributions to the 3 normal strain. So it's not becoming more normal strains, we have only 3. Okay, now this is a combined stress state, and actually superposition principle is possible, so we just can add up those. So we add up all of those and see what is epsilon given the reaction of, given the action of all 3 stresses in all 3 normal directions. What is the reaction tensor strain? Okay, and just adding it up gives you direct, direct, direct on the diagonal, so to say, and the indirect ones with a minus. Okay, so the initial cube in the deformed situation, it looks completely all sides different length. Okay, and in a case that only normal stresses are present, we are finished. We would be finished now. Unfortunately, we need also the shear stresses. Okay, so this is the first contribution. Normal stress leads to a normal strain. Clearly, you could have inverted that one. We could have put strain as action and stress as reaction, and I will show you later in the general case how that works. I don't do it here. Okay, now shear stress. What is shear stress doing? We take the undeformed cube from the beginning. It has its 3 lengths on the sides, and a shear stress, you remember, a shear stress is causing shear strain. That's what you could guess. And you remember that shear strain corresponds to a change of angle, a change of orientation of slides. So the cube will become a diamond shaped object dependent on which shear stress we apply. So for example, plotted here is shear stress sigma 1, 2 equal to sigma 2, 1, only acting on the other face. So the magnitude of the shear stresses is the same. And this thing is deforming the object, a cube, into a diamond from, if you look from the front. Okay, and the change in angle, this is this 90 degree minus gamma 1, 2 as we had defined yesterday. Now here, the action and the reaction are mediated by the shear modulus, which is not the same as the Young modulus in general. Okay, so shear modulus is the second material parameter. The Poisson ratio is also the second material parameter, and I will show you later that there is a relation between them in isotropic materials. Okay, so that was shear modulus. Shear stress is causing as action as shear strain. Now, in isotropic material, the Young modulus, the shear modulus, and the Poisson ratio are correlated with each other, and the correlation can be found via a coordinate system rotation, which is a little bit too much for today, but I will prove it mathematically at least without showing you the rotation transformation in detail. Now, I make a short break to see whether there are questions and take a breath. Goal was to find what is the relation between EG and nu in the isotropic elastic material. Okay, so you remember when we rotate the coordinate axis around the coordinate system around the 3 axes, then by an angle alpha, then we get x1, x1 prime, nu, x2, x2 prime, nu, and x3 doesn't change because we rotate around this one. Now, we take the simplest stress state which is there possible, and that is a linear stress, and that has only one stress component, all the others can be 0. This is a valid possible stress state. When you pull a piece of rubber in the one direction, sigma 1, 1 is only this. There are no shear stresses and there are no other normal stresses. Okay, so that corresponds to the first case. The action is the stress 1, 1, and the reaction is the strain 1, 1, and the strain in the perpendicular directions. Actually, rubber is a bad example. You can see here that when I pull, the band gets a little bit narrower, not very clear. And that is the meaning of the Poisson ratio. Okay, now this is normal stress only. So now how do we translate this into shear stress? We rotate by a certain angle and we see, sorry, this is the strain resulting from the action. Okay, and we rotate around the angle alpha and we see what happens. So take the shear stress component, that's the one I'm interested in. The diamonds here, the small symbols are just saying that I don't want to calculate all these things. And that means we need from the rotation matrix only the first row and the second column in order to calculate this. From the stress tensor, we need everything. So this is a trick to calculate one component on the left-hand side, not all 9. We don't have to do the work if it's not needed. Okay, and this means you have to practice a bit, that you can ignore quite some of the elements here. Okay, so carry this out at home, practice. I mean, you are at home, most of you probably. Practice this on a piece of paper later. I just show you the result. So this is the shear stress component, and the shear stress component in the rotated coordinate system clearly depends on the normal stress, but it also depends on the angle I rotate around. Okay, and now this I use as a reminder for you. In the original state, the stress had only normal stress. When we rotate, that means we change our face or our head. When we rotate, then we suddenly see a shear stress. And this is compatible with that what I said earlier. The stress state does not change by changing my point of view, but the components of the stress do change. So originally shear stress was 0. Now in the rotated state, shear stress is not 0. And this is what the rotation does to a tensor, even though the stress configuration itself does not change, but the components of stress do change. Okay. Now, we do the same for the strain. That one now looks a tiny bit more complicated. It has also the sigma 1, 1 cosine alpha sine alpha as the stress had before. Okay, and now from the definition of shear stress to shear strain, from this definition, we know that G is mediating between a shear stress and the shear strain. So if we insert the shear stress in the new configuration, and if we insert the shear strain, or if we want to see the shear strain in the new configuration on the left-hand side also, then we can read off the relation between 1 plus nu E here, 1 plus nu E, and the 1/2 comes from the definition of strain, which is 1/2 different from the angle definition. Okay, so for isotropic material behavior, shear modulus and Young modulus are related to each other uniquely. That means from the 3 material parameters, there's only 2 independent, so we can work with 2 only at our choice. We don't need the other one necessarily, unless it's needed for answering a question, which we might have. Okay, so that was the rotation of 2 tensors now. We did just something quickly. We rotate the stress and the strain, and in the new coordinate system, we have a shear stress to shear strain relation, and that one allows us to identify E and G, the relation with 1 plus nu on the denominator. Okay, that's nice. So isotropic material is simple. It has only 2 material constants. Now you remember, surely you remember, a gas has only 1 material constant, namely its compressibility. So elastic materials are different from fluids and gases. So they have at least two material parameters. Now, summary of the first section. Summary of Hooke's law. We take the strain as a consequence of various stresses. we take the shear strain, sorry, the angle change or the shear strains as a consequence of shear stresses for all these indices, for all these configurations, all three directions, all three phases. And now I want to show you how the stress-strain relation looks in index notation. How does Hooke's law look in index notation? Okay, now we bring everything together from the previous slide, and actually here the first indices show up. This sigma kk is the placeholder for the first invariant of stress, and that is sigma 11 plus sigma 22 plus sigma 33. So here, this one we don't have to spell out all the time, we abbreviate it. This nu divided by E you see here, and the 1 plus nu cancels when you take the second term. So the second term is this one, and the first term, this one is outside of the bracket, this one is inside the bracket, so that's the total first term. Okay, and I do this for all the other terms also, I don't explain it in all the detail again, and that gives us the three diagonal elements. So the left indices 1, 1 are reflected by right indices 1, 1 and kk, and that is not the same thing because sigma kk, do remember this please, I typically every year get this question again and again. Sigma kk is the placeholder for the sum of all three normal stresses. Okay, here epsilon 22, sigma 22, epsilon 33, sigma 33. At the end of the day, it could be that the strain on the left hand side and the stresses on the right hand side are related like this. And for I equals j, this works. So for normal stresses and normal strains, this is the Hooke's law relation in index notation. For shear stresses, let's see if it also works. For shear stress and shear strain, we also have an index 1, 2 left, 1, 2 right, 2, 3 left, 2, 3 right, and so on. So the relation here is actually simpler. For I not equals j, it's a simple 1-to-1 relation. Okay, so the 1-to-1 relation I can put in the first place. The second one for shear stresses is not like for normal stresses. So here I have still to do something. Okay, and what do I have to do? I put a delta ij. The delta ij, the Kronecker delta or the unit matrix, is actually making this 1 if we talk about normal stress components, and it's making this one 0 if we talk about shear stress components. Okay, so the 0 is good because I want to have a 0 for shear stresses, and the delta ij is a trick to do so. Okay, now the previous relation could not be true for another reason. It's not only that I wanted to have a matrix here. Before I had kk indices, which are dummy, and in the other terms I had ij indices, which are not dummy, which are free indices. So this term needed index ij anyway, and the delta ij is just doing the trick. Okay, now this is the stress-strain relation as it's on the formula sheet. This is Hooke's law in index notation, first two terms. And this one is just replacing the Young's modulus with the shear modulus, which is a possibility, as I had shown earlier. Okay. Now, the inverse will be the next, but again, I will do a short break. Let me see, how's the time? Okay, again, 1 minute break, one to 2 minute break. I don't want to be so specific. And then I will continue to invert Hooke's relation, and that was then section 5.1. That will have been then section 5.1. Oops, wrong screen. Up to now, we were talking as stress as the action and strain the reaction. Now I want to invert. I want to have strain as the action and stress as the reaction. I'm not sure what I'm doing. Okay, I want to see stress as up to now we were seeing stress as action and strain as reaction. The inversion means I want to see stress as reaction and strain as action, and that means I have to bring all sigma ij on the left hand side. Also the sigma kk should go left, should vanish on the left hand side, and epsilon ij, only epsilon ij should be on the right hand side. So that is what inversion means. And this is the law of Hooke in one of the representations as we had it before. Okay, so how can I invert a tensor equation? And this is something you will have to practice yourself. I show you the 2 tricks which are necessary for it, and then you can do it yourself. And this is fully symbolic. This is fully exploiting all the beauty of the index notation, because I mean, this equation is many, many terms, but in the index notation, it's very short. In the index notation, you only have to follow the rules, and then you can invert. Okay, so first trick is, what happens with this sigma kk term here? Okay, in the inversion, we can guess that there should be an epsilon kk. Okay, if we insert ij equals kk, then this one will also become equal to sigma kk, and on the left-hand side, we will have epsilon kk. So let's set ij to kk. Do this. And this is something which you have to do. This you will do many, many times. Because remember, what is epsilon kk? Epsilon kk is the sum of the normal strains. And that one is the small strain approximation of volume change I showed you last time. Okay, so we will often ask you, what is the volume change after a deformation? Okay, so then you will have to do this anyway. So let's do it for this equation here. Okay, we insert kk on the left-hand side for the indices, so that means we have to do it for all the terms on the right-hand side. Here, the first term is easy. That's then kk becomes the sigma kk is the placeholder for the first invariant, sum of normal stresses. On the second term, actually sigma kk is already there. That one does not change. That one directly follows. The delta ij becomes a delta kk, and here you must remember that delta kk is 3. It's a 1 plus 1 plus 1, the sum of the diagonal elements. Okay, that's it. And then we just bring the terms together, sigma kk, we take it out of the bracket, and what remains at the end of the day is 1 minus 2 nu divided by E sigma kk. And this is the relation between epsilon kk and sigma kk. Sigma kk was 3 times the hydrostatic stress. Okay, so if I apply a hydrostatic stress, it has as a consequence, it has a volume change. And this is the material parameter which mediates between it. And it's not written here, it's called bulk modulus. I should have added it here. So the mediator between isotropic stress, between hydrostatic stress and volume change is called bulk modulus. And that one again is different from shear modulus and from Young modulus, but they are related this way to each other. Okay, now rewriting Hooke's law is the second step. So take the sigma ij, which we have, and take the sigma ij here, which we have, and bring this one on the left-hand side. This is what this line is doing. There's nothing new. And then the only thing what we have to insert here is the sigma kk as we calculated it here. So this small guy goes in here. And then we have on the right-hand side only epsilons. And on the left-hand side, we have stress. So strain is action, stress is reaction. And that looks like this then, after you have rewritten it. First term is the Hooke's law for strain going to stress. And the second term is just replacing E by G as we did it before already. Okay, and it's a matter of taste with which one you work. Okay, so that was stress-strain relation before we had a strain-stress relation. Okay, and this is Hooke's law. The coefficients in the two are slightly different. So note that you cannot take one for the other. And this is tensor inversion. Tensor inversion is a little bit more complicated than simple algebraic inversion of a one-liner. This takes into account the full tensor nature of the object. Okay, now material parameters are E, nu, and the non-independent G. Some other people, Mr. Lamé, many more than 100 years ago, didn't like this. So he was taking an abbreviation. He was taking everything which came in this term together to lambda, and he was taking everything which was coming together in this term here to 2 mu. So his G and mu are the same thing, it's only a different symbol. And here, the lambda is actually abbreviation for many of these symbols. Okay. Now, after the break, I will continue with energy.